Hi, my name's Brian. In this video, I'll be discussing Newton's method, including an informal Newton's method derivation, initializing Newton's method, numerical analysis parameters, the residual matrix, and the tangent matrix. So we're going to be exploring Newton's method in the context of the time-stepping algorithm. So here we start off the algorithm and we step from 0 to n steps. Here we put things that change with time or need to be initialized before our Newton while loop. The variables that go here should not be in the while loop, or it's going to override the information on each iteration of the loop. If you don't initialize error here, then you can't enter the Newton while loop, and the code's never going to execute the loop. The variable it begins a counter. This prevents an infinite while loop, and that's going to prevent us from crashing computers. The variable cn holds information from the previous time step. This is an intermediate variable, and it will be useful in the Newton while loop, which I'll explain in a minute. So before we start the Newton while loop, we actually want to initialize our first guess for Newton's method. And then we have our conditions here. For Newton's method, we want basically this section of code to run while the error is greater than the tolerance that we've already defined, and the number of iterations is less than the iterations max, and that's going to cut any extra iterations so we don't end up with an infinite while loop. And for Newton's method, we're using an implicit version of our code basically to calculate acceleration when acceleration isn't a linear function. When we have a nonlinear acceleration, we have to apply Newton's method. So if we just take a step back and look at exactly what Newton's method is, we have this function g of x with some true root in green and some initial guess in red. And we know the function evaluated at g of x naught. We can calculate the slope at that point, g prime of x naught. We know that the error is the difference between g of x naught and 0, since we want g of x naught to be 0. So we can approximate the 0 by linearizing the function at that point. And we have a new guess, basically. And we can repeat the process. And we can see here that the error decreases by half after just one iteration. So if we just look at the linear equation for a second, we know the equation of a line is just y equals m times x minus h plus b, where h is a horizontal shift. And we plug in the values from our particular equation and set it equal to 0 since we are searching for the root. And then we can solve for x sub 1, which is our new guess. This is the equation for Newton's method, the general equation. So getting back to this pseudocode, we want to first increase our iteration counter. And if we take a step back and actually just look at our residual equation, that's g in yellow, we see that our equation of motion is actually dependent on our velocity. After we first iterate, we need to update our velocity since our acceleration changes and velocity is dependent on acceleration. This helps make our calculations more accurate. So the numerical analysis parameters here are shown at the right. If our residual depends on velocity, we're going to need to update the velocity after each iteration of the while loop. So then we're going to have this variable here, eta, and then we're going to need cn, which we can see for our particular equation of motion. Our velocity depends on, our acceleration depends on velocity, so we're going to want to update that. If we change acceleration, we need to update velocity. And similarly, if we have an equation of motion that's dependent on position, we're going to want to update position. We're going to want to use zeta, and then we're going to want to use bn instead of cn. And we can also have an equation of motion that's dependent on both velocity and position. So we're going to want to use both bn, cn, both eta and zeta, and both x and v. So here are just some intermediate variables defined for the particular projectile with drag problem. And then we have our residual here for the particle problem, which we can easily derive. So we have the FBD here. We have force equals mass times acceleration. We plug in the forces. We set the equation equal to 0. And then that's our residual equation. So we have G is the residual, and then A as a function of A. So that's what that notation means. And then as you can see, that's the same equation in our pseudocode on the left. So then next we have the tangent, and that can be calculated, or that needs to be calculated by hand, and the full derivations are shown in the course notes. So if we look at the linearized plot from before, we have our initial guess in red, the function evaluated at the point in gray, and the tangent of the function in blue, and that gets us our new guess shown in yellow. So again, we have red, and then gray, blue, and yellow, and all of those colors correspond. So then next we can calculate error. Error is the distance of that line. So we want g of x to be 0. So if it's not 0, that's the length of the line, which is why we use the norm function for error. And we can iterate the Newton while loop until we're satisfied with the error. So when error is less than tolerance, the loop will end. Next, we can execute trapezoidal rule. And this stays the same for every computing project, because once we solve for acceleration, we can just update velocity based on acceleration. And then next, we update our position. And then note that it works for any acceleration as long as we know the old acceleration and the new acceleration, since this is a numerical integration technique. So once we get the old and new acceleration, trapezoidal rule will always apply. And that's it for the time-stepping algorithm and Newton's loop in the time-stepping algorithm.